Hi, hello, welcome. This is Discrete Mathematics, and today we are talking about section 2.2, more methods of proof. This section we're going to talk about 5 different types of proofs. The first one is one that comes in quite handy, and that is a proof by contradiction. A proof by contradiction establishes P implies Q by assuming that P is true and that the conclusion is false. Then, using P and not Q, along with other axioms, definitions, theorems, rules of inference, etc., it derives a contradiction. And then we conclude that, well, what we assumed to be true must be false, and therefore Q actually must be true. A contradiction is a proposition of the form R and not R. A proof by contradiction is sometimes called an indirect proof. Indirect proof, because we are not directly proving the thing, we are proving that it can't not be the thing, so therefore it has to be the thing. Let's take a look at an example. Here in example 1, give a proof by contradiction of the following statement. For every n in Z, if n squared is even, then n is even. Let's think about what a direct proof would look like. If we were going to do a direct proof, like what we did in the last section, a direct proof, we would say something like n squared is even. So n squared is 2k. And I want to somehow get to say that n is 2l. But I can't really do a square root here because then I'm going to have a square root of 2 and a square root of k. And I don't really know what to do with that. So where do we go? I don't know. A direct proof isn't really going to help us that much. So let's instead try a proof by contradiction. So here's my proof, and I'm going to put in parentheses contradiction just to be clear of the type of proof that I'm doing. We're going to let n be an arbitrary integer. So this is who are we telling our story about, where n is, n being an integer is the domain. N is in Z. All right, so n is some integer. Now I'm going to assume that this is true and that this is false. And then we're going to develop our contradiction. Assume n squared is even and that n is odd. So we know things about odd and even. Since n is odd, we can write n as 2k plus 1 for some integer k. K is in Z. So let's square both sides. So we get n squared. See, now, I'm going to take a moment to pause. This is where we couldn't get with a direct proof. With a direct proof, we were starting with n squared, and it was really hard to get not n squared. Here in our proof by contradiction, we were able to start with something about n, and then square that and develop into n squared. So here we are at n squared, and then we've got, let's see, 2k plus 1 squared, which is equal to 4k squared plus 4k plus 1. And I can write this. I'm going to take a look at this, and I can factor out a 2. So I could write this as 2 times 2k squared plus 2k plus 1. And this right here is an integer. K is an integer, so multiply k by 2, it's an integer. Square k and multiply that by 2, that's an integer. Add 2 integers together, you get another integer. So now I have something of the form 2 times an integer plus 1. That is the form of something that's odd. So here now we see, so n squared is odd. And this is a contradiction because up here at the beginning, I said n squared is even. So this is a contradiction. Therefore, n squared, therefore, n is even. And that is the end of my proof. So that is a proof by contradiction. Assume that P is Q, or P is true, and that Q is false. And then you show, well, that you develop a contradiction And then you can say that, well, Q actually must be true. Okay, let's come to another one, example 2. Give a proof by contradiction for all real numbers x and y. If x plus y is greater than or equal to 2, then either x is greater than or equal to 1 or y is greater than or equal to 1. So I'm going to assume that this is true. Assume that this is true, and I'm going to assume that this is false. Just to note, before I get into my proof here, this is Q or R. So I want not, Q or R. This is x is greater than or equal to 1 or y is greater than or equal to 1. I want the opposite of that. I want that to be false. So that is actually not Q and not R. So that's what I'm going to assume, is that x is less than 1 and y is less than 1. That's what I'm going to assume here when I get into my proof. And then this is my domain. So I'm going to talk about that as well. All right, here we go. Proof by contradiction. This is not totally necessary to write that contradiction. I just like to be clear, especially when I'm writing proofs for students, to include as much information as I can that makes a reasonable sense. If you read the textbook, you read some proofs from the textbook, or you read proofs in other places, sometimes they can be a little bit terse, maybe, and not quite give as many details as you want. Sometimes when I'm reading proofs, I have to fill in some lines, right? Okay, how did they get from here to here? Is that true? And then I work it out. I'm like, oh, it is true. So I like to, when I'm working with students especially, try to include a few extra details just to be clear about how the steps follow one to the next. Okay, here we go. So we are going to talk about our story. Who is our story about? Let x and y be real numbers. I want to assume that x plus y is greater than or equal to 2. And, I'm assuming 3 things. That x is less than 1 and y is less than 1. So those are all the things that I said that I was going to assume. That my premise is true and that the conclusion is actually false. Since x is less than 1 and y is less than 1, let's add these together. So we get x plus y is less than 1 plus 1, which is x plus y is less than 2. Well, this is a contradiction because I'm assuming that x plus y is greater than or equal to 2. This is a contradiction. Therefore, either x is greater than or equal to 1 or y is greater than or equal to 1. Proof number 2 by contradiction complete. We're going to do one more. This is probably my favorite proof in this whole section. We want to prove that the square root of 2 is irrational using a proof by contradiction. Proof by contradiction. All right, here we go. So this isn't the traditional ones we've done so far, where we have a P implies Q. This is just all we're trying to prove is that the square root of 2 is irrational. So what we're going to assume is that the square root of 2 is rational. And if we know something's rational, then we can write the square root of 2 as P over Q for some integers P and Q, where Q is not equal to 0. That's what we can do with rational numbers, as we can write them as a fraction. We're also going to assume something else about P over Q. Every rational number can be written in lowest terms, so we're going to assume that as well. We are going to assume that P over Q is in lowest terms. And to be in lowest terms, that means that P and Q don't have any factors in common. If they had a factor in common, you could factor that out and cancel, and then it wouldn't be in lowest terms. So, i.e., P and Q don't have any common factors. Okay, so this is our setup. So if we know they don't have any common factors, we know that P and Q both can't be even. So P and Q are not both even. Then they would share a common factor of 2, which would mean they're not in lowest terms. So this means one of them is odd. They could both be odd, but I don't need to assume that. I just need to assume that one of them is odd. So let's see. We've got square root of 2 is P over Q. I can square both sides. And if I do that, I get 2 equals P squared over Q squared. And now I'm ready to, maybe I'll multiply those sides by Q squared. So P squared is 2 times Q squared. And that must be an even number. 2 times some integer is even. Thus, P squared is even. And we did in a previous proof, let's see, what example number was that? I think it was the very first one we did, example 1. We said if P squared is even, I think when we did example 1, we said if N squared is even, that implies that N is even. And now that we've proved a handful of things, we can use those things that we've proven in future proofs. So I've already shown in example 1 that if P squared is even, then P would be even as well. So I can use that here. Thus, P squared is even. We know that if P squared is even, then P is even. And again, I proved that in example 1. Okay, great. So, hence, I could write P as 2k for some integer k. And so now I'm going to start here. Let's see, I can write P as 2k. Let's square both sides again. Well, actually, maybe before I do that, I'll write, I also know that, oh no, I think I will square both sides right now. Let's do that, squared. So P squared is 2k, that whole thing squared. And what I know about P squared from up here is that P squared is 2 times Q squared. So I'm going to substitute that in right here. So 2Q squared is, let's see, the squared is going to square the 2 and the k, 4k squared. Let's divide both sides by 2. So that means that Q squared is 2 times k squared. Well, this means that Q is squared is also even. Now we see Q squared is even, which means Q is also even. This is a contradiction. Since P and Q are even, they share a common factor, and P over Q is not in lowest terms. And that's our contradiction. We said that we could write the square root of 2 as a rational number in lowest terms. This is a contradiction. Thus, square root of 2 is not rational. And that, oops, I guess I didn't draw close enough to a square. That is the end of my proof, ending it with a tombstone. So this proof is a proof by contradiction. And in this proof, I was able to use something I've proved previously. So that's the power of doing more proofs, is that you have more theorems and more things that you can use in your future proofs. So any proofs that we do in class, you can use when you're working on your homework. Okay, let's move on to our next type of proof, which is a proof by contrapositive. So recall the definition of contrapositive. P implies Q. The contrapositive is not Q implies not P. Sometimes P implies Q is difficult to prove, and it might be easier to prove not Q implies not P. So that's what we're going to try out here in example 4. Give a proof by contrapositive to prove that for all x in R, if x squared is irrational, then x is irrational. So this is P and this is Q. So let's go ahead and write down what the contrapositive is. Contrapositive would be if x is rational, then x squared is rational. That might be a little bit easier to prove. What we saw in example 1 is if we start with something that's squared, it's really hard to go somewhere from that. But if we can start with x, then it's much easier to square an x. So if we start with our contrapositive, we're able to start with something that we know about x, which is going to be a little bit easier than starting with something that we know about x squared. So let's get into our proof. And we're going to prove this contrapositive statement. So I'm going to suppose that x is in R, which is my domain. So this is who are we talking about, and that x is rational. Then x can be written as P over Q for some integers P where Q is not 0. That's my standard setup for rational numbers. I'm going to square both sides to obtain x squared equals P squared over Q squared. P squared and Q squared are both integers. So x squared is an integer over another integer. And I also know that Q squared is not equal to 0 because Q is not equal to 0. So this means that x squared is rational. And that is proof by contrapositive. Next one is proof by cases. So in proof by cases is used when the original hypothesis naturally divides itself into various cases. And in order to use proof by cases, we're going to need like a reasonable number of cases that we can write down and show. We're not really going to be able to show hundreds of cases, but if there's a reasonable finite number of cases, we can maybe look at all of those. This type of proof is sometimes called an exhaustive proof because we are showing this works or doesn't work for every single case. So we are exhausting all the options. Example 5. Prove that m squared plus 3n squared is equal to 40 has no solution in the positive integers. So here we're looking at m and n are positive integers. Then this does not work. So it's false for all positive integers m and n. That's what we're hoping to prove. So here's my proof, and I'm going to put in parentheses cases because we're going to show this doesn't work for any cases. Let's suppose that 2m squared plus 3n squared is equal to 40, and that m and n are positive integers. So we are going to assume that there are some solutions. Now let's try to find those solutions. And what we're going to end up showing is that we can't. All of the possible options for m and n together, none of those are going to work. So we're going to exhaust every possibility that could be if m and n were positive, and thus there are no solutions. So one way to show that there are no solutions is to look at every possible combination of solutions and say, look, there aren't any. That's this case's idea. So if we're looking at 2m squared plus 3n squared equals 40, and m and n are positive integers. So that must mean that m and n are positive integers, means they're greater than 0. So let's say, since m squared is greater than or equal to 0, and 3n squared is greater than or equal to 0, And I'm saying this because the smallest possible values don't allow this to be negative. We also know that if this was 0 somehow, then 2m squared could be 40 or something less than 40. It can't be bigger than 40. So we can set bounds upon what 2m squared and what 3n squared can be. So 0 is less than or equal to 2m squared is less than or equal to 40. And 0 is less than or equal to 3n squared is less than or equal to 40. We probably could say tighten these two options a little bit, but this is as tight as we really need to go to see what our possible cases are. Let's work with each of these inequalities. I'm going to divide everything in here by 2. So 0 is less than or equal to m squared is less than or equal to 20. And divide everything in here by 3. 0 is less than or equal to n squared is less than or equal to 40 divided by 3 is 13.3 repeating. So as I'm thinking about possible values for m and n, I'm trying to list all the possible values for m, all the possible values for n, and then I'm going to try each of those in my original equation. So let's see, 1 squared is 1, 2 squared, maybe I'll do this in another color because this is kind of like my off to the side calculation. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. So let's see, m can be between 1 and 4 because it has to be, m squared has to be less than or equal to 20. So if m was 5, then it would be too big. So that means that since m is a positive integer and 0 is less than or equal to m squared, 0 is less than or equal to m is less than or equal to 4, that must mean that m, it can be 1, 2, 3, or 4. Here's all my possibilities for m. I'm going to do the same thing for n. This kind of looks like an n. Let me write this better. Since n is a positive integer and 0 is less than or equal to n is less than or equal to, let's see, n can't be 4 because then it would be too big. So I'm going to go 3. N can be 1, 2, or 3. So now we want to check every case. There'll be 12 things that we're going to check. We'll check what if m is 1 and n is 1? Then is this equation true? What if m is 1 and n is 2? Is this equation true? So we'll check every single combination, and those are all of our cases. So here we go. Check the cases. So I'm going to make a big old table. Here's one row. Here's this one. So what I'm checking is 2m squared plus 3n squared. Is that equal to 40? I'll put all my values for m up here. M can be 1, 2, 3, or 4. And n can be 1, 2, or 3. So let's see. 2 times 1 squared is 1, plus 3 times 1 squared is 1 is 5. So that's not right. Let's come down here. Let's see, 2 times 1 plus 3 times 2 squared is 4, is 12, 14, still not right. So I'm going to go through and check all of these cases. 2 times 1 plus 3 times 9 is 29. Nope. Now we'll go to 2 times 2 squared is 4, plus 3 times 1, which is 11. 2 times 4 plus 3 times 4, getting closer, is 20. That's not big enough. I'm looking for 40. 2 times 4 plus 3 times 9. Ooh, closest one yet, 35. Still not right. We'll keep on moving. 2 times 3 squared, which is 9, plus 3 times 1 is 21. That's not big enough. 2 times 9 plus 3 times 4 is 30. Not big enough. 2 times 9 plus 3 times 9 is too big. 45. So close. Maybe here in this row we'll find one. 2 times 4. Oh no, whoopsie, sorry. 2 times 16 plus 3 times 1 is 35. 2 times 16 plus 3 times 9 is so close, too big, 44. 2 times 16, this is going to be too big, plus 3 times, oh, whoops, this is the 3 times 9, which is 59. Sorry, this is 3 times 4, which is 44. So none of these will work. I did not see, I was looking for a 40 in here somewhere. Does any combination work? And no combination worked. And I've tried every combination. Therefore, 2m squared plus 3n squared equals 40 is false for all positive integers m and n. And that is the end of this proof. Proof by cases. Let's do another one with cases. This won't have quite as many cases. Example 6. Prove that for every real number x, x is less than or equal to the square root of x. Let's write our proof. Let's let x be a real number. Let's remember some things about the absolute value. So let's do a little recall here. Recall that the square root of x is equal to x if x is greater than or equal to 0. So if x is a positive number or if x is 0, then the absolute value of x doesn't really do anything. It's just that number. However, if x is negative, then it makes that negative number positive. So like if I'm taking the square root of -3, I would do -3, which is positive 3. So x is equal to negative x if x is less than 0. So if it's a negative number, you negative the negative, which actually makes it positive. That's what the absolute value is doing. All right, so now that I know that, I see that there are two cases. If x is greater than or equal to 0, or if x is less than 0. So let's look at our cases. Case 1. If x is greater than or equal to 0, the absolute value of x is equal to x, which is greater than or equal to x. So I can flip this guy around and say the absolute value of x is greater than or equal to x. Yeah. So the absolute value of x is greater than or equal to x. So the absolute value of x is greater than or equal to x. So that we're seeing that the inequality holds in this case. Case number 2, if x is less than 0, then the absolute value of x is equal to negative x. Negative x is greater than 0. Negative x is greater than 0 because x is actually less than 0. So negative x is actually a positive number, which is greater than 0. And we know that 0 is greater than x because we're in this case right here. This case, everything is kind of the reverse of what you would intuit. So this is actually saying the same thing. So the absolute value of x is greater than or equal to x. In either case, the absolute value of x is greater than or equal to x. And that's what I was hoping to prove. I think we will pause this video here and we will do a second video for 2.2. So I will see you in that one.